this work, and this time it's going to be on the Avron-Exher-Last lattice, which I hope you're going to explain to us, right?
Okay. I will give review of several recent joint works of Professor Weinberg and myself about quantum graphs or optical networks. This is a part of our activity. We have grant, NSF grant, which is essentially financially supported by IBM and some other agencies. And what does mean quantum graph? This is limit of the system of very thin channels if the thickness epsilon goes to 0. But I will try to explain maybe more precisely what is going on here, because many features of quantum graph depends on this transition and depends on the particular boundary conditions. We have starting point is large system of the optical channels, thin cylinders. This is network of the cylinders. The axis of cylinders form the skeleton, one-dimensional skeleton, but this is a three-dimensional object. We have here cylinders. Assume that all the cross sections are the same, epsilon times c, but channels are connected by the junctions. The junctions have in reality different structures, and this is essential physical problem, how to connect together several 2, 4 or more channels. Corresponding procedure as well as the drilling of the channels is known as lithography, and I'm not expert here, but we have to understand that there are different junctions. There is one junction is like sphere, and second junction has another shape, but there are 10 or 15 different type of junctions. But inside this domain, d epsilon, this is a system of the channels. We must solve some wave equation. More precisely, we have something like this. We have first of all some system. We have here many channels which are branching and so on and so forth. But outside this system, we have several ingoing channels, and we can send some signal through such channels, and we have several outgoing channels. We can receive a response. And the central problem here is the solution of the scattering problem. Assume that we know wave which goes in through one of the channels, and it necessary to calculate what is going on outside, what will be response of the different channels. Finally, we must calculate the scattering matrix for this large system. But system can be highly complicated, and fundamental problem is to simplify such calculations and to reduce calculations to the quasi one-dimensional system instead of Maxwell equation or wave equation in the thin but three-dimensional domain. We want to study one-dimensional problem. Inside domain, we have, for instance, Laplace operator or Maxwell operator, and we have to study stationary scattering inside this network. But on the boundary, we have some boundary conditions, and physically, most boundary of this domain d epsilon on the surface of the cylinders. In the future, when we will pass through the limits, those boundary conditions will disappear. Physical condition is Dirichlet condition, which is the normal component of electrical field, must be 0 on the surface of each cylinder, which means that surfaces are ideal conductors. We have this Dirichlet problem, and it necessary to pass to the limit if epsilon tends to 0, but limit doesn't exist, because it's clear that in each cylinder the spectrum of Laplace operator started from the constant lambda naught over epsilon square. And here lambda naught, lambda 1, this is somewhere here, lambda naught, lambda 1, and so forth, are the eigen values of the cross section. We can consider cross section. This is two-dimensional domain. We can solve Dirichlet problem, spectral Dirichlet problem. We will find lambda naught, lambda 1, and so forth eigen values. And after scaling multiplied by epsilon, they will be lambda naught over epsilon squared, and so on and so forth. And the frequency or k squared must be between be greater than lambda naught over epsilon squared. In such channels, that frequency must be necessarily very high. And this is a asymptotical theory. We have to prove that solution of the scattering problem, or resolvent, which is more or less the same, of this in this complex domain, which is presented better here. It can be infinite or finite, does not matter. In this domain, resolvent asymptotically for small epsilon close to resolvent of some much more simple object. And this much more simple object is the system of one-dimensional intervals with branching points. No, roughly speaking, this is the skeleton of our optical network. Of course, along each edge we must get something like this. S squared equals k squared, psi equals psi. We will get such equation, usual equation, one-dimensional wave equation. But most important problem is to calculate what is going on in the vertices. But
just understand better the structure of this lattice. So
what?
To understand better the structure of this lattice, how do you continue this lattice?
No.
So
In the future, I will study infinite lattice.
okay, but
I will study infinite periodic lattice.
And
But it can be finite or
the lengths of these lines, do you want to keep them to be the same, or you want
What?
the lengths of the edges? Do you want
yes,
them to
I won't preserve the length of the edges.
You're gonna
Edges
say
will
so.
be the fixed, length of the edges are fixed, and epsilon tends to 0.
Okay.
But frequency necessarily k squared tends to infinity. But we are working in the so-called first zone. Spectrum of the cylinder, infinite cylinder, is absolutely continuous, but it has different multiplicities. Lowest multiplicity corresponds to the first zone between lambda naught, bottom and lambda 1. I'm talking mainly about this zone only, because above, situation will be different. I'm talking about gluing condition, what we must add here. But what kind of gluing condition we must add here.
Yeah,
This is the
so-
central issue.
Was is work by Robert Schrader and collaborators who determined all possible gluing conditions at the vertices compatible with self-adjoint.
Okay, I will formulate now. Okay.
Do you know that?
To understand what is going on the one particular junction, we must solve the following problem. Let us consider one junction with a scale epsilon is equal to 1. We don't want to pass to the limit here. Epsilon is equal to 1. Let's consider one particular junction which has some particular geometry. And let's consider infinite channels which are going into this junction. And for this system we must find scattering. We must solve scattering problem. That we send to one of the channels some wave which has the form exponent I k s. S is parameter along the axis times psi 0 of z, and psi 0 of z is the eigenfunction in the cross section with zero boundary conditions. This is an incident wave, and this wave after propagation through the junction partially will be reflected, partially will be transmitted, and it's possible to prove that there are asymptotics of the same form far enough from the junction. And as a result, we can define here the scattering matrix. And this scattering matrix for individual junction, which must take into account all geometric information about junction, it will provide the correct gluing conditions here.
And gluing conditions, is that boundary condition or what?
This is, yes, it will be condition. No, you can say this is, I don't want, what is a boundary here? You can say this is, I am talking about gluing condition, but you can call boundary condition. How such condition looks like? This is particular symplectic condition. Let's consider one particular vertex. We have this is one particular junction. We have of the limiting quantum graph. We have several one-dimensional lines going out of this junction, and then we have some function psi of s. Along each channel, along each line, we have parameter s or sj along the parameter sj. We can introduce, first of all, vector psi at the junction j. It's simply system of the limits of the function. If parameter s goes to limit from different directions. Generally speaking, function psi of s will be discontinuous here. And secondly, we can find for the same function psi of s limits of the derivatives along each line, again at the junction. We have two vectors, dimensional vectors, d-dimensional vectors, and d is the number outgoing channels from the junction. And gluing condition which reflects the property of scattering matrix here, because matrix A there and scattering matrix here are the same. It depends on the particular frequency, but this is frequency k. In reality, as I told you, has order 1 over epsilon squared. We have here a condition of the form that derivatives vector derivatives equal some matrix times vector of the limits of this function. And this matrix must be symmetric. This is, it means that I can understand this vertex as a system, this one particular junction, and system channel which going out of the junction. I can understand this equation near junction as a system of D equations which are connected by some delta potential in the origin. And this delta potential is related to this matrix A. Equation channels are connected because this matrix is non-degenerate. How to find this matrix A? It depends, I repeat once more, on the particular frequency. We are talking about K which between square root of lambda naught over epsilon and square root of lambda 1 over epsilon. And for such fixed K, this K depends on epsilon. For such fixed K, we must calculate this scattering matrix. And I repeat once more, scattering matrix depends only on geometry of one junction, but not on the rest. And mathematical theorem, which we published with Weinberg in Communication of Mathematical Physics 2007. It's a very recent, huge paper, and which contains several continuations. This theorem has the following structure. If we consider this epsilon network, if we select K between of such guys, K depends on epsilon, and if we remove from this interval, set of very small measure, exponentially small measure. Unfortunately, there are bad frequencies. There are a lot of different resonances between different junctions. Main approximation here is that boundary condition on each junction is independent on other junctions, but there are resonances necessary to exclude. If we will exclude set of very small measure, that optical problem, system of Maxwell equation or wave equation, the system of cylinders with Dirichlet boundary conditions, is close. Solution of the scattering problem or solution of the resolvent are close to the corresponding resolvents or scattering problems on the quantum graph. Quantum graph is a system of lines or intervals. Some of them can be finite, some of them can be infinite. Lengths of such lines are simply distances between different junctions on our skeleton, and in each junction we have gluing condition, symplectic gluing condition of such kind. Calculation of this matrix, it's problem which must be solved on the computer for each particular junction. In the theory of quantum graphs, and last summer, 2007, exactly here, we had again workshop on the quantum graphs. In the theory of quantum graphs, there is legend that most important and most typical gluing condition is the Kirchhoff gluing condition. Which means that sum of the d psi d sj, if sj tends to 0, that first of all function psi of s is continuous on junction. And secondly, some of the limiting derivatives, which I must calculate. For instance, in direction out of junction, this sum must be equal to 0.
So how do you, is the orientation important, or I don't quite
No,
understand?
I took orientation out here. No, it's like for the for the liquid. Amount of liquid you goes into junction and out must be equal. It's the
Yeah,
same.
but now you have, that's the source there.
What?
No, it's a direction in which he takes derivative.
Yeah.
I took derivative inside in direction of out, but or in doesn't matter. It's
S equals 0 corresponds to the verb.
S equal to 0 is the vertex, yes. I'm talking about S, but this parameter S, of course, is different. It's on different edges, I must select. Okay. And unfortunately, this condition is non-physical. It's not optical. This condition can appear and appears in the following situation. And this is probably explanation of this legend about very special role of the Kirchhoff condition. Assume that we have very system of very thin cylinders, and inside I consider a parabolic equation du dt equals delta U, but with Neumann boundary condition. Du dn on the boundary d epsilon equals to 0 with reflection. This parabolic equation, of course, has solution, and this solution, solution of this parabolic equation, fundamental solution, gives the transition probability of the Brownian motion inside this domain with reflection. Now it's clear that if epsilon will tend to 0, that this Brownian motion, this process has a limit. Projection of the Brownian motion on the skeleton is not Markov process, but in the limit of epsilon tends to 0, you will get limiting process. And this limiting process will be 3 one-dimensional Brownian motion on each ray, on each edge, with some gluing condition inside, and this gluing condition for equal channels will be exactly Kirchhoff condition.
So in terms of the trajectory, what would it mean?
What?
How would the trajectory go, this one-dimensional Brownian motion? How would it go when it enters the junction?
This is when it enters the junction, roughly speaking, with probability 1/3 is it goes
1/3.
out 1/3 symmetrically, of course, if you have such guy. No, in more general form, it can be some coefficient proportional to the thickness, but my assumption was that all channels are completely symmetric.
And does this matter? I mean, what if we've drawn things very symmetrically on the board, but if the channels are, you know, in some extreme direction, the same thing?
Yes.
I also have another question.
Generally speaking, here we must take some constant. If you have Neumann boundary conditions, the gluing conditions, the limit epsilon tends to 0, equals sum of the constant. Now, of course, if you something, it will be somewhere very narrow, probably that reflection in this direction will have small probability. But if you have symmetric junction, channels of the same thickness, situation will be completely symmetric, coefficient will be 1/3. There are some probabilistic papers, Friedlin, Wenzel, and others about this stuff. But I repeat once more, this is Neumann boundary condition. Spectrum of Neumann boundary condition started from 0. But we are talking about here Dirichlet when everything goes in the area of very high frequencies. For the practical, for real junctions, typically function psi is discontinuous. There are completely different boundary condition, but I am not ready now to discuss problem about how matrices, real physical matrices A looks like. I don't know. And as a result, I will discuss today only simplest case, because in this case it's possible to calculate everything. And now I want to define this Avron-Exher-Last model. This model has the following structure. We have a graph, which vertices is usual lattice ZD, neighbor nearest vertices connected by unit intervals. Along each interval we have natural parameterization, length parameterization S. Of course, it's necessary to use S with some indexes to describe different edges, but I will use one letter S. And the Hamiltonian H naught is negative second derivative with respect to S squared plus Kirchhoff gluing conditions. And this Kirchhoff gluing condition, they are written above. This is the B. Sum of the derivatives with respect to no, 2D. It's not D, it must be 2D, because there are 2D directions. Sorry, it must be 2D. Sum of the limiting derivatives is equal not 0, it's a particular case, but it's equal constant times value of the function psi on the junction, and function psi around junction must be continuous. This is slightly more general than Kirchhoff. Instead of 0, I can add here some constant A naught. We depend on junction times psi at the point junction. This is generalized Kirchhoff condition. Assume, first of all, that A naught is constant. This is a periodic situation. This is a periodic periodic operator. We have quasi one-dimensional manifold with branching, and we have, of course, natural parameterization S on each interval, length parameterization, we have Lebesgue measure, we have L2, and this is self-adjoint operator in L2. This operator is unbounded, of course, because we have here second derivative, and this operator is periodic because there is natural group of translation acting on this Hamiltonian. And it's possible to present, and this is true, not only symbolically, but true under if we introduce correctly concept of the delta function on this graph. That H naught, this simply negative Laplace operator, one-dimensional Laplace operator. This is the second derivative with respect to S, plus A naught constant times sum of the delta functions located on the vertices. It means that this is an operator, this periodic operator, Schrödinger operator with periodic potential. If A naught is equal to 0, it will be classical Kirchhoff condition. If A is not equal to 0, this is the operator with potential. I will assume that A naught is positive, because this is exactly natural assumption probabilistically, but maybe it's not. Do you have any questions about model?
Yeah, I don't quite understand. So you have a periodic one that you described, right?
Not periodic, because graph is periodic.
Yeah, and your boundary conditions are all the same at the vertices.
The same. A naught is fixed right now.
Now, what's this thing you have in the box down the bottom there? That looks like something I didn't catch.
It's written here that this operator can be understood in the following form. You have
In one dimension or in more dimensions?
no, this is operator d2d squared is you can say it's one dimensional, but we have s on each edge.
Okay.
This is quasi one dimensional. It's it's three-dimensional graph with quasi one dimensional
Okay.
structure. Each edge is one dimensional, but system of edges is three-dimensional or multi-dimensional lattice. On each vertex we have this gluing condition, the same. If A naught is equal to 0, then we have what? We have minus second derivative with respect to s squared. For this operator, if we consider du dt equals d2u ds squared plus condition the sum of the psi prime of 0j plus minus is equal to 0. J from 1 to 2d. Assume that we consider this equation with this condition, A naught is equal to 0. Then this operator, this parabolic problem defines Markov process on this graph. You can say this is a Brownian motion, but this is some kind of combination of Brownian motion and random walk. On each edge you have what? You have usual one-dimensional Brownian motion, but transition between edges, it's symmetrical random walk. If you consider this process, and this, what is written here, this is the generator of this process. This process has a very important property that behavior of this process on large values of t is like behavior of the three-dimensional Brownian motion, because the lattice is multidimensional. However, locally, for small t, it behaves like one-dimensional. And this is very important, and we will see this duality between one-dimensional behavior and multidimensional behavior in the future. But I want to say also very briefly that there is natural generalization of this model which is also can be at least mathematically very interesting. We can consider models with potential which is the derivative of delta function. In each vertex we can put derivative of the delta function. What does it mean? It means that our function psi in the neighborhood of given junction differentiable and has a limit. Derivative has a limit in all for different direction, and all such limits are equal. It's shown picture in one dimension. You have one function decreasing exponentially to the right. Delta prime we have at the point 0, second decreasing to the left. Derivative of the upper function and of the right branch and lower branch are equal, and both are negative. But function has different limits. Function by themselves has different limits between different directions, and sum of the limits over all directions equals b naught times this common value of the derivative. This is delta prime.
Okay, I just want to understand still one thing. So I think I understand this, but I'm not sure because I'm confused by the notation.
Yes.
So your function psi, it lives on the edges of.
Yes. This is this function.
It's a function on each edge.
Yes. If you consider fixed edge, then you can say this is direction S1, this is direction S2, and so on and so forth. And you can consider this function on 4 different half axes near this point. And you can ask, what are the limits of this function for different directions? You will get 4 numbers. This is what I called vector psi. At the point 0 and 0 indicate particular junction. And I can study also derivatives, all derivatives.
All derivatives, yeah.
Yes, and I can find limit of the derivatives. The vector gluing condition is the symmetric relationship between one vector and another vector, symplectic. And this is a delta prime. Limits of the derivatives are the same, but limit of the function are different. And sum of the values of the function it will be not on this common value of the derivative. If you consider one-dimensional, elementary one-dimensional Schrödinger equation, second derivative, minus second derivative, you can define this derivative outside point 0 by usual formula, second derivative. This is on the function which are 0 in the neighborhood of point 0. And after this you can ask, what are the possible self-adjoint closures, extension of this second derivative? This is a problem about point, what can be gluing conditions. And delta prime, as well as the delta, are 2 standard gluing conditions. This is the, and there are some others. And now I want to formulate results mainly due to probably Exner about spectrum of this operator. But I am talking about a spectral series of Avron-Exher-Last lattice, periodic, when I naught is fixed, and talking about delta case. But sometimes in the future I will use. How to study resolvent on this lattice, quasi one-dimensional lattice. No idea, of course, is very trivial. Let us assume that we have a function psi of s on our graph. We can consider restriction of function psi of x on the vertices only. Psi of x belongs to z, d. And after this, on each particular edge between vertices x and x prime, you must solve equation second derivative equals case of psi equals k squared psi. With 2 boundary cases. It's so-called 2-point problems. It's not always solution not always exists. But you can trivially solve this problem, and you'll find that if you know value of resolvent of any or eigenfunction on the vertices, then you can reconstruct uniquely inside. There is some exact formula. This is elementary calculations. You can construct psi function inside the edge if you know boundary values. When you will, after this, for fixed point x, repeat the same construction for each edge leaving point x and apply our boundary condition, you will get the following equation, which is inside the frame. This is a bridge between continuous model with continuous s and discrete model. If function psi satisfy equation is psi equal k squared psi, then restriction of this function psi on the lattice satisfies this equation. We have, on the left part, we have usual discrete Laplace operator in symmetric form, but in the right part we have psi of x with some coefficients which contains a naught and contains frequency k. This is like potential, but potential depends on the energy. And because of this possibility to reduce problem on the continuous graph to the problem on the lattice. This is solvable model, of course, and exactly spectrum of this equation inside the frame is given by condition that coefficient in the right part less than 2d. The gaps are given by opposite inequality. And after this, on the k-axis, axis of the frequencies, you can solve trivial inequality for fixed A naught. I'm talking about periodic problem now. And you will find the following extremely nice answer. And Exner made this calculation for different, not necessarily square lattice, and he made some numerical experiments and so on and so forth. Now, first of all, on the k-axis, on the axis of frequencies, our periodic problem, we depend on the single parameter A naught, has infinitely many gaps. In contrast to usual periodic Schrödinger operator, which has only finitely many gaps in dimension 2 or more, we have here infinitely many gaps. And for instance, gaps with number n has, for large n, has asymptotic 2 pi n, and 2 pi n minus A naught over 2 pi n d. D is the dimension. But this is on the frequency axis. But if you consider squares, k squared, that is lambda, that on the energy axis, this delta n will have fixed length asymptotically. It means that we have here have not only gaps on the energy axis, but non-vanishing gaps. And this is very important because all attempts in the theory of photonic crystals, but I have no time to discuss optics, are based on this fact. To construct a realistic model, they are trying to approximate optical system by the quantum graph. They are drilling some thin channels in the silicon and so on and so forth. But and photonic crystals are exactly crystals with gaps.
So these gaps, unlike a regular smooth periodic potential where the gaps are going to go down very rapidly, let's say in one dimension, the gap width goes down very quickly.
Yes, but if you consider one-dimensional with periodic delta functions,
Then it's different.
this it will be non-vanishing because this is a particular case. And it means that if you consider, instead of the delta function, something very sharp potential, that many initial gaps will be long. Of course, it will vanish, but maybe far enough. It's very important to get wide enough gaps. In this case, we need not simply, we need strong contrast in optical properties. That means that constant A naught must be very large, roughly speaking. Okay, and spectrum of this periodic problem outside gaps we have bands, and spectrum is absolutely continuous. But what is highly important, that in this spectrum of this periodic problem, there are very special labels. Namely, if you consider frequency which n pi, when all my sine and cosine, let us return to this. If k we will 2 pi n, cosine will be 1, sinus will be 0, and we have exactly 2d. This is a point on the edge of the spectrum. And such points are the points of the belong to the point spectrum of infinite multiplicity. It's like very similar phenomenon to the Landau label or something like this. And if we fixed frequency n times pi, that there are infinitely many eigenfunctions, and all the eigenfunctions have the following structure. It's typical structure. You can consider, no, in my case, on two-dimensional lattice, some closed path, and after this you consider function psi which is equal to 0 outside this path, but on this loop, on this trajectory, it must be sinusoidal function which change directions. And you can substitute and you will see that it's the eigenfunction. Spectrum is not purely absolutely continuous. And because of the presence of such points, of infinite multiplicity, we have highly unstable spectrum. Very small perturbation can easily produce point spectrum. And my time is expired very fast, and I want maybe formulate several results. And maybe I will concentrate mainly not on the localization theorem because it's more or less standard, on different issues. And let us consider the problem about local perturbation, which is also very important in optical application. We have this periodic graph, periodic quantum graph, periodic Hamiltonian, and assume that we perturb locally. The question is, what can you say about localized states? What kind of localized states we can get? In the multidimensional case, there are two famous estimations: Zwickel, Lieb, Rosenblum, and Lieb, Tiering. This is above. This is a classical Schrödinger operator. And the question is, what is the number of negative eigenvalues? Assume that, and the answer is that number of eigenvalues less than some constant depends on the dimension, pi to some degree, and if dimension greater than 3, negative part of the potential to degree d half, 3 half in three-dimensional case. This estimation, Lieb estimation, it's optimal in the sense that if you consider coupling constant, that for small sigma and for large sigma it gives the correct answer, correct order of increasing. If well is deeper and deeper and deeper, then a number of negative eigenvalues will increase, and exactly as the coupling constant to degree 3 half in the direction 3. But Lieb-Tiering estimation is the sum of the negative eigenvalues to some degree gamma. Also very important estimation is the stability of the matter and so on and so forth. And Lieb published several papers with application of such estimations. But the question is, what is going on if you consider Laplace operator not necessarily in Euclidean space? We made recently with Weinberg analysis of this question. Assume that we consider Laplace operator on the graph, discrete graph, or this quantum graph, or on the group, and so on and so forth. And we proved that such particular form of the Lieb Tiering estimation or Lieb Zwickel estimation relate to the fact that Brownian motion in multidimensional space is self-similar. But if we have no such self-similarity, if behavior of the process for small values of t and for large values are t different, then the answer will be different. No, for instance, simplest theorem is the following. Assume that we consider Schrödinger operator on the lattice, classical Schrödinger operator on the lattice, and we have potential. Assume that potential is negative. The question is how to estimate correctly number of eigenvalues. And the answer here is, correct answer here is that you have to divide values of the potential onto large values of the potential and small values of the potential. On the set when the potential is less than 1, you have to take negative part to degree d over 2. It's like in classical Lieb estimation. Because this means that corresponding eigenvalue are formed by long range behavior of the potential. But if potential is very large, that everybody knows that if we consider one delta function on the lattice with arbitrary high magnitude, that we will get only one embedded eigenvalue. And it means that values of large values of the potential is necessary to take without integration. You have simply count number of the large values of the potential with some constant C1 and C2, which must be selected in optimal way, which depend only on dimension and depends on this threshold, which I took 1 here, but I don't want to. And such kind of estimation related to the fact that random walk has completely different behavior for small values of t and for large values of t. For large values of t, it behaves like three-dimensional Brownian motion, but for small values of t, transition probability, it tends to 1. Probability from 0 to 0 at a small time, it will be close to 1.
And why the second term is finite?
But what?
Why the second term is finite? Why if it's finite number of x? It's greater than 1.
No, assume that you have 3 delta functions on the lattice.
3, yes, I understand. But if you have kind of translation invariant potential,
No, but it's sufficiently deep.
so you assume it's compact support or?
No. No, this is estimation. If number of the point where the where our potential is greater than 1 will be infinite, that we can expect that spectrum must be infinite. No, like in the leap estimation, we assume that this integral is equal to infinity. This is what can you say in this case?
There's some kind of normalization problem involved.
Yes, but the question is how to select good thresholds is another story, which I don't want to discuss now. In reality, it is necessary to take not 1, but particular level. It depends on behavior of single delta function on the lattice. But important fact is that we have here in this leap type estimation, in general leap type estimation, 2 different contributions. One from the small values of t, because proof of leap estimation or leap tearing is probabilistic based on the different tricks with Cas-Final formula and so on and so forth. But in this Cas-Final formula, you have to take you have to distinct contribution of small values of t and large values of t. This is exactly what is going on. And but in the case of the Avron-Exher-Last I will formulate 2 results. There are many such results, but typical result. Assume that we have A0 is equal to 0, no gaps. This is the case when we have operator H0 corresponds to the Brownian motion of this graph. And assume that we add some potential and assume that potential is constant on each edge. This is very natural in some applications. Piecewise constant potential. On each edge we have some constant. Then number of negative eigenvalues, if A0 is equal to 0, edge of the spectrum is 0, negative eigenvalues will be integral over S over set where potential is less than 1, negative part to degree d over 2, like in leap estimation. This is the large time behavior. Plus integral over v of s to degree 1/2 over such edges where this constant potential is greater than 1. No, of course, the integral will be sum because potential is constant. And this 1/2 corresponds to the so-called Localisation estimation. In the theory of one-dimensional Schrödinger operator, there is no good estimation for the number of negative eigenvalues. You can open any textbook, you will find 100 theorem, but Each theorem covers very small particular situation. There is no such more or less universal good estimation like Lieb, Rosenblum, Zwickau. Nothing similar. And this is, and the reason is, it's clear because one-dimensional random walk is recurrent. But here we have something like this. This is Calogero type. It corresponds to the one-dimensional so-called monotone potentials. But if you consider completely different result, if you consider delta prime model, which unfortunately I didn't explain in details, but it has very long gaps, then in this case any small perturbation, local perturbation, adds at least one eigenvalue in each gap. One local perturbation produces infinitely many eigenvalues in each gaps. And they appear due to presence of these points of the point spectrum of infinite multiplicity.
Wait a minute, how do you add the randomness here? How is it put in?
There is nothing random, it's not random results.
What did you say?
Yes, about random I will say last slide.
No, I want to understand what you just said because I didn't get it.
Yes.
So what you said about point spectrum and gaps. What was
I told you that if you have infinitely many gaps, this is a potential, this is the situation with delta prime potential. It's longer gaps. They are already long enough in delta case, but in delta prime much longer. Then in this case, if you perturb, you feel any local perturbation. Arbitrary is small.
What does it mean, local perturbation?
No, it means that you add on some edge some potential.
Okay, just one edge.
Yes. Yes, or in one vertex you can add delta potential, something like this.
Okay.
Then it will produce in each gap at least one eigenvalue. On the lattice, if we perturb lattice Schrödinger operator in one point,
Yeah.
and this point and the perturbation in the multi-dimension will be small enough that nothing will happen. And here, if perturbation is small, I cannot say you that there are eigenvalues below bottom of the spectrum. No.
But inside.
But inside gaps, because gaps, edges of the gaps are highly unstable. Presence of this point of infinite multiplicity. And last slide. Assume that we consider this model, it's number 4. That we have this second derivative and random gluing condition. That means that constant A, which I called A naught, now is different for different edges. And this constant is such constants in Kirchhoff type gluing conditions are independent identically distributed random variables. More precisely, I'm talking about case when Aj is A naught plus sigma A tilde and A tilde with zero expectation, some identically distributed random variables. This is Anderson type model.
So you have random boundary conditions.
Only random boundary conditions. You can add the potential, but again, I repeat once more, you can solve on each edge and you will shift these randoms to the edges. This is the most principal. And here we have the following result. In both cases, when we have delta or delta prime potential, when we have gaps. And for arbitrary coupling constant sigma, we will get zones of localization inside each gap. It's not strange because even one local perturbation produces already many such gaps. We have some localization in the gaps, but also we have localization of the bands. But localization of the band depends on the sigma. roughly speaking, for all bands which are below level sigma or sigma over 2, like on the usual lattice, we have localization. But again, what does it mean, localization on the bands? I cannot guarantee that there is localization everywhere in the bands. Let us look one more time on this fundamental formula by Exner. Where is this formula by Exner? It's somewhere here, probably. Yes, this. Let us look at this formula one more time. If k is very close to the edges, to the point pi n, then cosine sine will be equal to 0, and this randomness will be with very small coupling constant. As a result, near the edges of the bands we cannot. Maybe there is localization, but we cannot prove this localization, as we cannot prove localization around point 0 in the classical lattice Anderson model. Because perturbative methods are not working, but inside gaps we have the same situation. Special point n pi, when we have infinite multiplicity and we have high instability, unfortunately and very strange, can be covered by perturbative theory based on the use direct large coupling constant, or perturbative theory based like Spencer or Eisenman, when we apply inverse operator inside the gap. But anyway, we have here the same difficulties near critical point, like in the problem of localization for Landau labels. It's time to stop.
Thank you very much. Questions or comments?
I have a question. It goes back to the very beginning, because you mentioned that the actual gluing conditions depend upon K.
What?
The gluing conditions that one actually gets depend upon K.
Okay.
Although you didn't use K-dependent gluing
Yes,
conditions.
yes. This is it.
This seems to mean that you actually
are
don't
complete.
have a
Look.
subjoint operator. Or is
No, no. You have to understand the following, that you have this lambda naught over epsilon squared, and you have lambda 1 over epsilon squared, and you have here lambda tilde over epsilon squared. I want to study my resolvent near this point, but our theorem with Weinberg covers large neighborhood, which contains many eigen values. It means that the optical system includes infinitely many Anderson models on the graph for different, because I calculate, I can here add plus minus O of 1 over epsilon. And in such this neighborhood, we proved that there is gluing condition which independent on this guy. But here we have many eigenvalues. Yes, you are, of course, completely right. This is, you can say, mathematically speaking, it was only some kind of introduction, that there are optical systems which can be transformed asymptotically to the study of the quantum graph. Boundary conditions, this quantum graph, you are completely right, depends on the particular selection of this parameter lambda tilde in the first zone. But for instance, in the second zone, if you consider second zone, it will be already quantum graph on the space of the vector functions, and but corresponding gluing condition will be completely different, much more complicated, and nobody studied what is going on there. But because asymptotic theory works in such neighborhood contains many increasing number of the eigenvalues, we can say that to some extent this activity about localization are related. But I don't want to say that localization is very important for the optics phenomenon of localization. As a mathematician, we study this phenomenon. But right now, it's not the time to discuss localization in this optical application, because accuracy of the manufacturing of the channels is extremely high. And channels are relatively short. They can be considered as ideal. There are some difficulties with junctions. Junctions are much more complicated issue. Maybe randomness on the junctions in the boundary condition important. But however, the question of stability or instability of some optical effects, it exists, but it's not. Physicists did not ask yet about localization. This is our.
That's the usual problem by now, because
But
usual problem. So people make more and more perfect devices, and therefore no chance for stability.
Yes, but they are perfect. But if we will consider in the future really large system like optical computers, because they are talking mainly the central application must be optical computers, then in this case, of course, total length will be comparable to 1 over epsilon, and the problem of stability will be highly essential. Right now, this is a relatively small experiments. It's not important. Okay. Yes.
Sorry, just a historical comment. Among those who first introduced the model was Coulson, I think in the 40s, graphite, and then Montrol, especially developed the model, I think, got to see already this result of Exner that you mentioned, and I don't know the work of Exner. But Montrol published in Journal of Mathematical Physics a number of papers.
No, maybe this is extremely yes, and we tried to find. I am probabilist, and I tried to find who was the first who proved that Brownian motion, a system of thin cylinders with reflection, converges to the motion of the graph. It's very difficult. It's like soliton. Novikov tried to find who invented soliton, probably Jacobi, because at least after paper, maybe Smelansky or maybe Avron-Exher-Last. Exner is physicist. He published many papers about such lattices, the spectral theory, and so on and so forth. But at least after this physical publication, the mathematical theory started of what we call today quantum graphs. And our activity with Weinberg about passing to the limits is exactly, in some sense, mathematical problem to justify. Maybe for physics it's more or less 100% clear that process is the system of thin fibers close to the process on the lines. But mathematically it's not so trivial, and naive formulation, I want to stress, is wrong, because it necessary to exclude something. Okay.
Very much.
Thank you.